Hello guys, I'm trying a new setup today to do you a lecture starting chapter 14. Okay, so we'll see how this method works. Now, we're starting chapter 14, and in this chapter we're looking at the first concept of reaction chemistry. Okay, we learned last semester how to write a chemical equation to express a chemical reaction. The example you can see on your screen is hydrochloric acid aqueous reacts with sodium hydroxide aqueous, and it goes to sodium chloride aqueous in water liquid. Okay, this is a stoichiometrically balanced chemical equation, so we can use stoichiometry to calculate the possible amount of product that we can get if everything reacts. Okay? But we're going to dig a little deeper. And we're going to ask questions like, how long do I have to wait to get product? Is it a fast reaction? Is it a slow reaction? Can I speed that reaction up? Can I slow that reaction down? How much product can I really expect to get for this reaction? Is it possible to get 100% conversion to product? Is it not? If it's not possible to get 100% conversion, how much can I get? Okay, will the chemical reaction happen on its own, be spontaneous? Or will I have to force it to happen? Is it non-spontaneous? All of these questions are going to be important if you are a chemist trying to develop a new process or a chemical engineer trying to tweak a process so that you get maximum product for minimum cost. So we're going to start with, here in chapter 14, our study of what controls the rate of a chemical reaction. Okay? So we want to predict how much product we can get as time goes by. So how long do I have to wait to get this much product? How much long do I have to wait to get this much product? The study of a rate of a chemical reaction and the factors that affect the rate of a chemical reaction is called kinetics. Okay? So, kinetics is the study of a rate. The rate is the change of some variable with time. Okay? Like speed, miles per hour. So right now, on our highways, the upper speed is 70 miles per hour. So that means that your change in distance per unit time should be 70 miles per hour. Or if you were paid, you're paid, let's say, to babysit $10 an hour. So that's the rate of money earned per unit time. Okay? So, in chemical reactions, we're going to be interested in how concentration is changing with time. So we're going to look at change in concentration with time. Okay? Now, if we want to look, well, I'll write that out for you in a minute. So we're going to start here by talking about factors that can affect the rate of a chemical reaction. Okay? We're going to look at it qualitatively. Qualitatively means without numbers. So the most important factor in how fast a chemical reaction happens is the nature of the reactants. Now, nature means things like structure, polarity. This plays the biggest role in how fast a chemical reaction happens. And it's something we can't manipulate, okay? We can't change it. The nature is the nature. If you want to manipulate that, you're going to have to figure out new reactants. So an example, okay, coming over here and looking at the screen, would be something like comparing the reaction of HCl with NaOH to make water and sodium chloride, and we're interested in making water, and compare that with taking hydrogen and oxygen and making water. This reaction, the acid and the base reacting, happens blink of an eye. Okay? The minute you bring them together, they initiate. the reaction of hydrogen and oxygen to make water is very hard to initiate, so it's very hard to get started. We have hydrogen and oxygen in the room with us right now. I don't see little water droplets just magically forming in the air. Okay? So different reactions have different rates based on the nature of the reactants. Now, another factor that can affect the rate of a chemical reaction is concentration. Okay? Think about it. For a chemical reaction to happen, the particles, the reactants, have to find each other, and they have to actually collide with each other. So if you have a really low concentration, they have trouble finding each other to collide. Okay? If you have a high concentration, it's easier to find each other. You have a higher number of hookups per unit time. So rate is proportional to concentration. The higher the concentration of reactants, the faster the chemical reaction. Now, this also brings up another really important point. Over the course of a chemical reaction, the reaction slows down because reactants are being converted to products. Okay? Things slow down with time. So, if we think about time zero, okay, we got all purple reactant molecules. And a little while later, some of them are changed to green molecules. And then a little bit later, more green, less purple, and then more green, less purple, more green, less purple. But you know, in this first unit of time, we converted 1, 2, 3, 4, 5, 6, 7, 8 of them. And we have 1, 2, 3, 4, 5, 6. Let's see, 1, 2, 3, 4, 5, 6, 7, 8 purples. Now, in the next unit, the 8, only 4 of them changed over because I had fewer purples to change. And then of the 4, 2 changed over, and then I have the 2, 1 changed over. Okay? So we have a change with time. Now, I'm going to draw a graph here for you. Okay? Where's my eraser? Now, so I'm going to put concentration here, time down here. So we started out with 16, okay, at time 0. At the first time spot, I'm down to 8. At the next time spot, I'm down to 4. So 16, 8. In the next time spot, I'm down to 2. And then in the next time spot, I'm down to 1. So look at this. I've got a curve of concentration versus time. So it's not a straight line. This tells me that the rate of the reaction is changing as time goes by because my concentration versus time graph is not a straight line. Okay? And notice that the slope is getting smaller. Okay? That's another indication that the rate of the reaction is decreasing. Now, let's think about physical state. Okay? The chemical reaction happens because of collisions between particles. We're going to talk about this in great detail near the end of the chapter. But as we look at collisions, okay, you have to have particles that are moving. The particles have to be able to be mixing. So at least one of the reactants has to be in some kind of mobile phase. The gas phase, the liquid phase, the aqueous phase. Okay? If we have a solid that's interacting with a gas or a liquid, the greater the surface area, the more possible points of contact with the liquid or the gas, the faster the reaction. Think about burning a big log and getting it to start to burn versus a piece of paper. Okay? Paper, flat piece of paper, lots of surface area, burns very quickly. A scrunched up piece of paper, not going to burn as quickly. Okay? Another factor that affects the rate of the reaction is temperature. As temperature increases, the particles are moving faster on average. Because remember, temperature is connected to average kinetic energy of the particles. So it's connected to how they're moving. Okay? So as temperature goes up, the number of collisions per unit time goes up. That means that the rate of the reaction should go up because you're having more collisions per unit time. Now, lastly, okay, we come up to the catalyst. A catalyst always increases the rate of the reaction. And a catalyst is something that facilitates the reaction, but is not used up over the course of the reaction. So it's always sitting there. Okay? There are different kinds of catalysts, but, example would be enzymes. Enzymes are catalysts. So we'll talk about catalysts at the end of the chapter, the very last thing. Now, let's talk about expressing a rate of reaction. Rate means change in something with time. Okay? So, for a chemical reaction, we're going to look at change in concentration of time. So, if we started looking at a graph, kind of like the one that I was looking at earlier, okay? On our y-axis, we'd have concentration. Now, we're going to show concentration as the reactant or the substance, the chemical agent inside square brackets. That's going to represent concentration. Then we've got time down here. So concentration is a function of time. Okay? And normally in a chemical reaction, we're going to get something that looks like that. So rate is going to be seen as change in concentration over change in time. Delta in math means change. Okay? So here I've got the change of a reactant A, and let's say that I've got the reaction A goes to B. Just very simple reaction. Okay? Now over time, as the concentration of A goes down, the concentration of B should go up. So if I were to draw what was happening with B here, B would start out as 0. B would go up as a function of time. So this is B. So if I had another thing over here, concentration of B with time, and I was showing them both on the same graph, concentration of B goes up, concentration of A goes down. Okay? Now, if I looked at, I'll look at delta A. Okay? Between 2 points here. So that's A initial, A final. And there's our delta T. Well, excuse me. This should be T initial, T final, and this would be A initial, A final. Okay? So if I looked at delta A here, A initial minus A final, I'm going to get a negative value because A final is lower than A initial. If I look at delta B over the same time interval, so that I have B initial, B final. B initial minus B final. I'm going to get a positive number. Okay? So change in concentration of the reactants is negative. Change in concentration of the products is positive. Now, if I look up here at our reaction, okay, A going to B, Stoichiometrically, they're in a 1-to-1 ratio. So one of the things I know here is that the change in concentration of A make a mess. Okay, the change in concentration of A has to be equal, well, the magnitude of the change in concentration of A has to equal the magnitude of the change in concentration of B. And my stuff is starting to get messy here, so let me give a little room here. Okay? The absolute value of the change in concentration of A has to equal the absolute value of the change in concentration of B. Okay, they're the same magnitude. They just have different signs. Now, if I want to talk about the rate of the reaction, I could talk about the rate of the reaction in terms of the change in concentration of A or the change in concentration of B. And as we do this, we want to think about how we like to do math. We all know we like positive numbers better than we like negative numbers. Okay? So let's look at this for a minute. If I want to express the rate of a chemical reaction, and I want to do it in terms of positive numbers, then I could say that the rate of the reaction just equals the rate of change of B, which is a positive value, the change in B as a function of time. But if I want to look at it in terms of the concentration of my reactant A, then I would say my rate of reaction equals negative the rate of change for A as a function of time. Okay? And this is because we want positive values. So I can say the rate of the reaction equals the rate of B, which equals the negative rate of A. Because change in A is negative, change in B is positive. Okay? Now, let's look at a graph again and talk about how we look at a graph and how we get rate. So we're going to look at the change in concentration of A with time. Let me draw my graph again. Concentration of A. Time. We get this curve. Now, if we think about rate, okay, delta A over delta T. Rate on a graph like this is rise over run. Okay, rise over run. So if I pick 2 points here, rise over run is the slope of the line that connects those 2 points. If I were to pick 2 other points here and look at rise and run there, I get a different straight line. What we're looking at when I take large time intervals like this is an average rate. So if you look at my first line here, I'll call this rate 1. Now look here at rate 2. I can see that rate 2 is smaller than rate 1. and the rate is changing with time. Now, as I said a minute ago, these are average rates. What we want to move to is an instantaneous rate. An instantaneous rate is a rate at a moment in time. Okay? Delta T is very, very small. So if we started looking at taking smaller and smaller delta T's, so instead of going between here and here, I go between here and here. And then I get smaller and I go between here and here. And I get smaller until I get to a single point. Okay, so my point, I'm going to put my point of interest kind of in the middle of that. Straighten things out a little bit. When I do an instantaneous rate, okay, I'm going to get the slope of the line tangent to my curve at one point. So I'm going to try to draw my best line in here. And of course my red marker is dead. Try this one. All right. So we get things that are different. Now I'm going to show you a pretty graph, one out of the book. Okay. Here's a reaction, the decomposition of ozone. Well, the ozone reacting with C2H4 to give us oxygen and C2H4O. Okay? And here's the graph of the concentration of ozone as a function of time. B would be the average rate of the reaction over the time period shown. Well, excuse me, yeah. C is the average rate of reaction over 10 minutes. D is the average rate of reaction between 30 and 40 minutes. You can see how they're different. Okay. A is an instantaneous rate. It's only tangent at the initial point of the reaction. Okay. So A is an instantaneous rate. B, C, D, and E are all average rates. All right. Now, I won't move it so fast, I promise. Sorry. You can see up there on that graph, okay, one more time, that all of these rates are different, and they're all for the same reaction. So we want to know which rate of reaction is going to be most important for us to use. And for us, instantaneous initial rates are the rates that we want. We want rate is the point in the reaction where we actually have the most information about concentrations and the conditions in the reaction vessel. So as we study kinetics, we're going to use instantaneous initial rates. Okay? Now, as the reaction proceeds, and we'll start talking about this more in chapter 15, as products build up, reactions can actually run in reverse. So as the concentration of product builds up, you start to see two reactions happening in the reaction vessel. The forward reaction and the opposite, the reverse reaction. At the initial point of the reaction, only the forward reaction is happening. So that's another reason why we want to concentrate in on the initial instantaneous rate. The instantaneous rate at time t0. No reverse reaction is going on. Okay? Now, let's look at another reaction. We had a reaction that had an A going to B. Now let's look at a reaction where two reactants react to produce a product. So hydrogen plus iodine going to hydrogen iodide. Okay? Now, if I look at this, for every hydrogen that we react, we're going to get two hydrogen iodides. So that means the rate at which hydrogen is disappearing is different from the rate at which hydrogen iodide is appearing. Hydrogen iodide is appearing twice as fast as hydrogen is disappearing. Okay? So if we want to think about how these two relate, the rate of hydrogen iodide appearing is equal to 2 times the rate of hydrogen disappearing, 2 times the rate of iodine disappearing. And notice that there's a negative sign here, right there. Okay? And a negative sign right there. And that's because, remember, the change of hydrogen concentration with time and iodine with time is negative. The rate at which hydrogen iodide is appearing is positive. Or we could say that the negative the rate of hydrogen change with time is equal to 1/2 the rate of hydrogen iodide. Hint, that's going to be important to us. Okay? So, if I want to communicate to somebody else the rate of my reaction, what do I tell them? The rate of hydrogen, the rate of iodide, the rate of change of hydrogen, the rate of change of iodine, the rate of change of hydrogen iodide. Okay, we want positives, okay? And we want to communicate as clearly as possible. So what we're going to do is we're going to have to take into account the coefficients in the balanced chemical equation. Okay? Each reactant we know has its own rate of appearance and disappearance. We know that the magnitudes are related to each other. So let's look at a Joe generic reaction. Little a of A plus little b of B goes to little c of C plus little d of D. So I know the rate for A is the change of A is a function of time, the rate for B is change of B, so on and so forth. And we want to have a positive rate of reaction. We know the change or the rate of change of reactants is negative and rate for products is positive. Okay, and they have different coefficients. So what we're going to want to do here is we're going to want to normalize. We want a rate is positive, okay, and we're going to divide the rate of each component by its coefficient in the balanced chemical equation. Multiply by -1 for the reactants to make them positive, okay? So let's look at this. The rate of the reaction then for this reaction is going to be a -1 over little a, the rate of A, which equals -1 over little b, the rate of B, which equals 1 over C, the rate of C, and 1 over D, the rate of D. If we change rate out for the delta symbols, so I can say a -1 over A, change in A with time, equals -1 over B, change in B with time, which equals -1 over C, change in C with time, and not -1, 1 over C, change in C with time, 1 over D, change in D with time. Okay? So, let's look at this reaction. 2 hydrogen sulfides react with 3 oxygens to give us 2 waters and 2 sulfur dioxides. If the change in sulfur dioxide concentration is 2.3 moles over liters times seconds, what is the rate of the reaction? And what is the rate of change of oxygen? Okay, guys. So what we're told, okay, is that the change in sulfur dioxide concentration with time is equal to 2.3 moles over liters times seconds. And it asks us what the rate of the reaction is. Well, in this balanced chemical equation, the rate of reaction is going to equal 1/2 the change in concentration of sulfur dioxide with time. Okay? So 1/2 of 2.3, got my calculator, 2.3 divided by 2. So this equals 1/2, 2.3 moles over liters times seconds, which equals 1.2. It's 1.15, but I have to round to two significant figures. Moles over liters times seconds. So that's my rate of reaction. Now, the rest of the question says, what is the rate of change for oxygen? Okay? Well, I know that the rate of the reaction is 1.2 moles over liters times seconds. Now, in terms of oxygen, the rate of the reaction is equal to a -1/3, the change in concentration of oxygen with time. So I can go 1.2 moles over liters times seconds is equal to 1/3 the change in concentration of oxygen with time. Okay, I'm going to multiply through by 3. So 1.2 times 3. I get, and it's a negative there. So I get a -3.6 moles over liters times seconds equals the change in concentration of oxygen with time. And that's the rate for oxygen. Okay? It's not hard. Don't beat yourself up over this. Okay? You can look at the conceptual problem 14.2 on page 591, and you can look at problem 28 on page 627 in your book, and you can do some more examples of this. Okay? Now, once we've calculated the instantaneous rate, what's it good for? Well, the instantaneous rate is the first step to getting us to something called a rate law, and then we're going to go from a rate law to something called an integrated rate law, and they're all used to help us try to figure out the collision by collision process of going from reactants to products. Okay? So let's talk about a rate law. Okay? At the heart of all kinetic studies is something called a rate law. It's going to be an equation that expresses the rate of reaction as a function of temperature and concentration of reactants and products. Now, a rate law is an experimentally derived equation that relates the rate of a chemical reaction, the concentration of the components at an instant in time, at a given temperature. It's kind of a snapshot for a reaction. Okay? It's just boom. This is what it's doing right now. This is what the rate's going to be under these conditions. So any prediction that we make about a chemical reaction has to conform with the rate law. At the rate of the reaction at the instant the reaction is initiated. Now, why do we want to use that rate? Well, the initial instantaneous, I mentioned velocity earlier. Okay. All right, guys, we were interrupted and I was talking about rate law. Now, before we do the rate law, just want to remind you, if I have a reaction, little a of A plus little b of B going to little c of C and little d of D, then the rate of the reaction could be calculated based on the concentration change in any one of the components of the reaction. Okay? The rate of the reaction is equal to -1 over little a, the change in concentration of A with time, that's rate for A, or -1 over little b, change in concentration of B with time, 1 over C, change in concentration of C in time with time, or it could be equal to 1 over D, change in concentration of D with time. Okay? And now we can write that for any one of the components of reaction. And I did that problem for you. So we're ready to talk rate law. Now the rate law is an experimentally derived equation. which means I can't look at the chemical reaction and derive this equation. I have to do experiments and get data to get this. Okay? It relates the rate of a chemical reaction and the concentration of the components at an instant in time at a given temperature. This is a snapshot equation. It tells us what's happening at one instant in time. It's going to help us to predict things that are happening at the molecular level. Okay? And any predictions we make have to conform to the experimental rate law. Okay? Now, to derive the rate law equation, we have to do a series of experiments. What they are is we do the same reaction over and over again with different amounts of starting materials, different amounts of reactants. Okay, so they have differing concentrations. Okay? Now, we're going to be holding the temperature constant in what we're looking at, because we're going to talk about temperature later. So right now, all we're going to do to these reactions is run them at different concentrations. So if we have the reaction little a of A plus little b of B going to little c of C plus little d of D, then the rate law would equal rate is equal to K, concentration of A to the M power, concentration of B to the N power, and if there were more reactants, we would include them as terms here. Okay, raised to a power. K is called the rate constant. It has a specific value at a specific temperature. You change the value of the temperature, well, you change the temperature, you change the value of K. So K is where temperature shows up in the rate law. M and N are called rate orders. Okay, and they define how the rate is affected by a concentration change for a specific reaction. K, M, and N are all experimentally determined, and they're determined from calculations based on the experimental data and can never be determined by inspection of a balanced chemical equation. Okay? The sum of N and M is called the overall rate order. The most common individual rate orders are first order, which is a power of 1, second order, a power of 2, or zero order, the power is 0. But you can have rate orders that are fractions or negatives. We're just going to avoid those. So, if we looked at a simple rate law for a reaction A going to B plus C, rate equals K, A to the N. If N equals 1, the process is first order, and if the initial concentration of A is doubled, the rate would double. If N is 2, if the concentration were doubled, the rate order would quadruple, because anything, you know, if I doubled it, 2 squared is 4. If it's 0 order, if the concentration is doubled, nothing changes, because anything to the 0 power is just 1. So here's a pretty little graph from the text. Okay, let me get the graph. Okay, here's a simple 0 order process. You can see that concentration of the function of time gives us a nice straight line. If it's first order, it starts to curve. If it's second order, it curves more. Okay? If we look at rate versus reaction concentration, if it's 0 order, it's a flat line. If it's first order, okay, it's a flat line, but it has a slope. And if it's a second order, it's a curve. Your book really loves graphs. Okay? Note, for 0 order, concentration doesn't affect the rate. So let's look at a problem, 14.3, on page 595 in your book. So if we look at page 595, and yes, I'm flipping to the page. I didn't have it open already. Problem 595 says the reaction A going to B has been experimentally determined to be second order. Okay? So rate equals Ka squared. The initial rate is 0.0100 molarity over seconds at an initial concentration of 0.100 molar. What is the initial rate if A equals 0.500 molar? Well, in this problem, we've got rate at a specific concentration, so we can find K. Excuse me. Once I have K, then rate at my new concentration is just K, the new concentration squared. So my rate is 0.250 molarity over seconds. Now, let's talk about how we get a rate law. Okay? It all starts with a series of experiments or runs of a reaction that are performed with different starting concentrations for the reactants. From these reactions, we determine initial instantaneous rates. Now, we're going to do this experiment in lab next Tuesday, okay, next time we meet. And we're going to be getting instantaneous initial rates. From instantaneous initial rates, and we do a series of experiments. So we do multiple reaction runs. From these instantaneous rates, we obtain experimental data of concentration and initial rates, and that's how we're going to determine M, N, and K. So let's look at how we determine M, N, and K. These are all just math skills. Okay, you'll be given a chart that shows initial concentrations and initial instantaneous rates. To determine M, a rate law for substance A, okay, if I have a rate equals K, A to the M, B to the N, I want to choose two reactions where the concentration of the component B is the same, and the concentration of A changes, which allows us to do some math tricks, okay? Namely, I can say the rate of experiment 1 over rate of experiment 2 equals K, A to the, A1 from reaction 1 to the M, B from reaction 1 to the N, divided by K from reaction 2 to the M, B from reaction 2 to the N, okay? If the concentrations of B are the same, then they're going to divide out. Okay, so this and this are the same. They're going to divide out. That gets me rate of experiment 1. Oh, and the K's divide out because they're a constant. Okay. That gets me rate of experiment 1 equals A from experiment 1 to the M. And if I divide it by the rate of experiment 2, then on my other side I have A from experiment 1 to the M, A from experiment 2 to the M. Now, if I have two things raised to the same power, I can take the power outside. Okay, I get rate from experiment 1 over rate from experiment 2 equals concentration of A from experiment 1 over the concentration of A from experiment 2 to the M. Now, usually at this point, okay, right here, you can look at this number and see how they're related. If these numbers are the same, then M is 1. If this number is this, if you look at this number and you square it and you get this number, you know it's 2. 0 is pretty easy to identify also, okay? Now, if you can't do it by inspection or you're not comfortable doing it by inspection, you can use log. If you take the log of the left side of the equation, that has to equal m, the power, times the log of the concentrations. Okay? And you get in the same way because you choose two runs where the concentration of A stays the same and the concentration of B changes. Now I've written it all out here again, okay? To get K, you plug in the concentration of N and M from one expression